Okay.
Okay, we are officially recording. And it's 3 o'clock, right on the dot. All right, welcome to our computer science learning event for April. We're focusing on computational thinking for this session. And we would like to welcome you. And I will introduce myself. My name is Janine Nakakura. I'm a resource teacher on the computer science team at OSID. And this is my colleague, Faith Ishihara. She's an educational specialist with the computer science team. I'll let her say hi.
Hi, everybody. Thanks for joining us.
And let's say hello to Terry. Hi, welcome.
Hey,
All right,
Terry.
just in
So
time.
good to see you.
Next slide. So here is our agenda for today, and it has all of our links and the slide presentation and anything else you would need for today or from today. And I will put that into the chat so you can have access to our slides and any other resources that we talk about in this presentation. So there is the agenda in the chat. So we would like to start off with, what do you know about computational thinking? Okay, so I'll give you a few seconds to ponder that. And we're just kind of doing a formative assessment to see what you know or don't know about computational thinking. And hopefully you will walk away with more knowledge about computational thinking. So what do you know about computational thinking? Put your answer in the chat if you can. And we will go to the next slide while you're thinking. What we will do is we will put the responses from the morning and the afternoon into this slide presentation so that those who are watching the recording can see what was in the chat. Okay, because you can't see the chat in the recording. Okay, so we will do that. So Terry says computational thinking is problem solving steps or algorithms that a computer could execute. Okay, you know what? She can just teach this session.
Yeah, let's switch places.
Yeah, I'll just sit back and listen to you. Okay, thanks for sharing, Terry. And
Awesome, Terry.
we will see how knowledgeable Faith is. Okay, so we're gonna do this pre-test to computational thinking, and you can use it. There are 10 questions, and we're not going to do all 10, but Faith already answered the first one. What is computational thinking? And she said it's using a set of techniques and approaches to help solve problems. So if you answer all 10 questions, you will find out whether which ones you got correct or which ones are incorrect. And so we won't tell you the answer. You'll have to take the quiz on your own and find out what the answers are. Okay. And hopefully, if you give this as a pre-test, hopefully after you do your training or teaching, that you give this as a post-test and everyone will get 10 out of 10. Okay. So next slide. I'm going to turn it over to Faith.
Okay, thanks, Janine. Yeah, so we found this Venn diagram that shows how computational thinking, computer science, and code all are related. And it's kind of important to recognize that computational thinking is both central to computer science and also widely applicable throughout education and the workforce. So here are the four strategies of computational thinking, and Janine found some really nice short to the point videos about them, but we can only show one. So which one jumps out at you? Like really calls and says, "Watch me."
Abstraction?
Oh, good choice, Terry. Excellent
Abstraction.
choice.
Funny. You should say that. Okay, doke. Let's watch the video on abstraction. I'm going to turn off my camera and mic and get that going.
Abstraction is a problem-solving tool that helps you to simplify a situation by removing unimportant information and focusing on what is truly important in a given situation. Suppose you want to find the best bus route between 2 points in a city. There is a lot of information to sort through. However, not all of it is important for this task. For instance, the location of tourist attractions is not important for plotting a route. So, when building your abstraction, you might choose to ignore that information. Highways and streets that buses do not travel along are also not helpful, since our goal is to find a bus route. So, you might choose to exclude those. Names of neighborhoods are also not important for this task as well. In the end, as the abstraction designer, you might decide that the most important information is simply where to get on the bus, which bus to get on, where to get off the bus, what times to get on and off, and the general shape of the route within the city. These pieces of information, bus number, start, stop times, and route, are essential to the task and are included in the abstraction. Note that even though it features only 5 pieces of information, those 5 pieces can represent many different routes, because every one of them has a start, end, route, bus number, and times. Because abstractions focus on the key pieces of information, they are doubly useful. A single abstraction can represent a whole class of similar things, and they make it easier to understand each one, because there is not extra information present. Every abstraction is built with a purpose in mind. For example, here are 4 different maps, visual abstractions of a city. This map is useful for finding city neighborhoods. This map is useful for finding city streets. This one shows the public transportation of the city, and this one helps them find major attractions in the city. All of these maps show the same city, but each map uses the concept of abstraction to remove what is unimportant and focus on what is important to the user. Abstraction is the process of creating an easier to understand version of a complex system by focusing only on key information.
Yay. So thanks for watching that. We kind of selected that one because of all the terms. Abstraction is maybe not a term you hear every day. So let's see, get to and here's some practices. Computational thinking is at the heart of computer science, and later you can take a closer look at the practices 3 to 6. And we found this infographic that shows how all these thinking strategies come together into one problem solving process. So first you break down your problem into its parts, and then you find patterns within that, and then you abstract the unnecessary pieces and what is important, and finally you come to an algorithm based on the most important information. So can computational thinking be taught beginning in the really early years? Yes, it can, and we'll give you a few examples of that today. So, if we take a look at the 4 strategies: decomposition, breaking problems down; pattern recognition; abstraction, finding the key pieces; and algorithms. So, let's look at the number 5 in math. What might, how might we decompose the number 5 for young students? So, what are those elements or smaller parts? Oh, yes.
Carrie says 4 plus 1.
Awesome. Awesome. Excellent. Okay. So here's a game that students can play to kind of reinforce their understanding of the possible variations of what makes up the number 5. Thank you. And where might we find patterns? Share some ideas in the chat.
In nature,
Absolutely. Yeah.
tiles on the floor.
Oh,
Oh,
wow. I
Terry.
love it. Yeah.
Great,
So,
great, great, great responses in the chat. Thank you.
uh-huh. Terry has caught on to the idea patterns are everywhere. It's the books we read and the patterns in the stories, patterns on fabric and paper and dance steps. And when you string bees with students or build blocks with them, you're helping them to recognize patterns and using that vocabulary along the way, decomposition, pattern recognition, helps them to have the language to share with you some of their thinking. And abstraction. So this is a example that works with little ones. Like we're thinking about adopting a pet. So we may not necessarily need to know exactly what types of food each pet would have, but if we abstract all the and we come up to the conclusion that all pets need tender loving care, they all need a forever home and to have their basic needs met. And algorithms. So here's an example, making origami, being able to follow step by step instructions. And this is also great for visual, spatial um, recognition. So maybe having students talk about the steps to get from their classroom to the cafeteria, or how do they get ready for school in the morning? What are the steps to take? Or baking cookies, can they follow a recipe? Or making a PJ sandwich? And my friend was telling me she asks her little one, her daughter, to describe the algorithm to folding clothes. So they incorporate it into their daily life. So let's see. Oops. Oh,
Faith, Faith,
uh
Faith.
hello. Are you am I
I,
still there?
I can hear
Can,
you, but
oh yeah,
turn your camera back on, Faith.
it is on.
No, it's not. I can't see you.
The green light's on. I see myself.
You
Oh,
know, this is the same thing that happened last week. Seriously, this happened last week. Okay, wait.
okay.
So
What did
I
we
can
do
hear
last
you.
week?
I can hear you. Let's break this down. I can hear you, but
Uh-huh.
we can't see you. Can see yourself?
Yes.
Terry, can you see her? No. Okay,
Oh.
so Faith's video isn't working. What steps can we take to help her solve this problem? Do you have any suggestions? Terry, you can turn your mic on or you can type it in the chat. But oh, this is a bad time right during our learning event, Faith. Oh boy. This happened last
Is the
week.
camera icon turned on?
Yeah.
You
And
might need to like jump back out and jump back in.
oh, I think that's what we did last time, and it actually
Oh,
worked.
let's follow that
So
pattern. You
yeah,
know,
there's
we
a
did that
pattern
last
there.
week.
Pattern
Yeah.
solving
Okay.
my
Oh,
problems.
wow, that
Oh,
worked.
I'm back.
Wow. So wow, that was fast. Wow,
Thank you,
amazing.
Terry.
Thanks, Terry.
Oh, that was
Um,
amazing.
so we did use computational thinking, right, to solve this problem. Right? We broke down the problem. Okay, it wasn't her sound, it was her camera. We could hear her, but we couldn't see her. And we know it's a pattern because seriously, we're not making this up. This did happen last week. So we said, hey, let's use this as part of our presentation. So yeah,
Yeah,
she
I
went
saw
out and came back
myself.
in and it worked.
Yeah.
And then decomposition, like I know Faith always has tons of like thousands of tabs open. So I always ask her, Faith, how many tabs do you have open? And she always says, I did clean them up. And then the algorithm, right? Terry said, well, check the camera icon, right? And the next step is you might have to go out and come back in. So let's go down this list
Hmm.
of steps. And we did that. And voila, it worked. So
I
thanks.
love it.
Yes.
Teamwork.
Yes. So we used computational thinking to solve that problem. And we'll type some responses into the slides for those of you watching the recording. Okay, so now we're going to do a game. And this is one of the activities we had on choice boards. Was it last year during the height of the pandemic? Or was it the other year? I can't remember. But if you click on the link above, we organized our choice board activities for computer science by grade level. So if you just click on the grade level, you can find all of the activities for your grade level. So let's go to grade 5, for example. Okay, so if you go to grade 5, it'll take you to all the activities for grade 5. So we're going to do a sample from grade 5. I think it's the one during week 8. So we'll go back to our slides. And in week 8, this is the offline activity I found. And so it says that puzzles are a fun way to develop computational thinking skills. So invent your own rules and algorithms for solving the puzzle below. And there's a standard that it's associated with. And what we would like you to do is convert the word Lisp into the word Java in 5 steps or less. Okay, and the rules are you must only change one letter of the word on each step. And on every step, it has to be a real word in the English dictionary. Okay, so you're going to go from Lisp to Java, and you can only change one letter at a time. And it must be a real word in the English language. And because we are short on time, we'll put a hint into the chat. Okay, so I'm going to put a hint into the chat. And if like Terry's really smart, I know, so she can figure it out in her head probably without the hint. But if you need a hint, I put it into the chat. Okay. Because Faith and I tried it. We practiced, rehearsed it, and it wasn't as easy as we thought. So we put a hint into the chat. And those are some words you could possibly use. You could actually come up with your own solution. There's no one solution for this, I think. But there is an answer key. And we did look at the answer key. And just to save time, we put the words that you could use into the chat. So llama, limp, lava, and lamp. So what order would you go in? If you start with Lisp, and you can turn your mic on, Terry, if you want. If you want to tell us what you're doing.
Can you change more than one letter? You can only change one letter.
One at a time.
So that means after Lisp, I have to keep 3 of those letters
Yes.
in the same place.
Yeah. That's a good point too. The letters have to stay in the same place, except for the one letter that you're changing. Yeah.
Okay. So sorry. The hints then are not for the next word.
Those are the 4 words you could use to go from Lisp to Java, but they're not in order. So you're going to have to figure out, okay, from Lisp, what word would go next? So talk us through your thought process.
So then the next one might be limp and change the S to an M. And then I'm thinking lamp.
Explain why lamp.
You would change the I to an A.
Okay.
So then you'd have LA. And then the other, and then from lamp, see, 1, 2. So from lamp, though, llama is 2 L's.
No. This one is 1. I don't know. Just.
Okay.
Yeah, that's what I said too. But yeah.
So then I would do llama because then it's LAM and you change the P to an A. Then you would go to lava and change the M to a V. And then you'd end with Java by changing the L to a J.
Very good. Yeah. By the way, the llama here is like the Dalai Lama, not the animal llama. Yeah,
okay.
I had to look that up too. You're correct. So very good, Terry. Can you tell us how you used computational thinking to solve this puzzle?
So you have to break down the word by letter. And then kind of think about, okay, if I can only change one, right? So I actually started from the end and I looked at Java and I thought, okay, I know lava, right, could come right before Java. So then I knew that was going to be my second to the last word. And then knowing that lava was the second to the last, L stayed the same. So so then I knew all the words were going to start with L, right? And then I just had to figure out backwards, like, okay, so if I eliminate a letter each time, what word is that going to give me? So it was weird because then when I started at the end, I jumped back to the top because then I knew L had to be right. And so then I went, oh, okay, it has to be limp because then you have LIP. The only other word letter that's different is the S and the M. So just process of elimination after that.
Thank you for sharing your
Fantastic.
thought process. I didn't think about like they all started with an L, and that's a pattern you noticed, and you broke it down and you started at the end, and yeah, you the computational thinking steps that you took out all the unnecessary information also. You said I'm going to start at the end because I know that Java and Lava are similar and they all start. So anyway, thank you for sharing your thought process, and hopefully you use your computational thinking cap to help you solve the problem. And if you want an easier problem, there's one in the slides before, and there's one a more challenging one after. If you want to something you want something a little more challenging. So
And
let's go to the next slide.
I shared that with my friend, and she also went from the bottom up. Interesting. Great
Yeah,
minds think
that's a good
alike.
strategy. So computational thinking, not only can you use it to play games, but you can use it in content areas, um, such as math or science, social studies, ELA. And, I'm a science teacher. So I always had my students write down the procedure for their lab experiment. And that is an algorithm, right? The process. So you can integrate computational thinking into the different content areas. And we also want to let you know, as we always do, that computer science is more than just coding. It's the 5 core concepts. And today we kind of focus on algorithms and programming, but there are other areas that we focus on. And we'll go to the next slide. So just to show you that the 5 core concepts, they go down on the left-hand side, and going across in this progression chart are the different grade bands. So you can see where the different standards fall in the core concepts. And some of these you're doing already, like writing the step to a procedure. That's computer science, but you can also do that in math, right? Or science. And then here are our standards. So impacts of computing, core concept number 5. We have 3 standards we covered today. And let's go to the next slide so you can see in more detail. This is the first standard: decompose or break down the steps needed to solve a problem. And Faith did that. We said, how can you decompose the number 5? Okay, for example. And the next one: compare and refine multiple algorithms for the same task and determine which is the most appropriate. So that was, Terry, when you were solving that problem. There are different ways to solve, that puzzle, and which is most appropriate. Everyone has different ways of solving things. So, we learned from listening to your solution, and then I systematically identifying and fixing problems, like when Faith's camera didn't work. How did we figure out what to do? We used our computational thinking and did some troubleshooting, okay? And got Faith's camera working again, like that, okay? So I'm going to turn it over to Faith so she can share with you an ebook.
Yeah, so this particular book is Computational Thinking and Coding for every student. Um, I really enjoy this book. It has lots of printable online resources. It's very engaging with simple explanations, and you can borrow it from our statewide ebook collection with these steps right here. And we also have audiobooks in that collection. So take a look. And today's word is computational. So I think Terry is the person with the most letters in her first name
Terry's
that
the
are
winner.
in common
Yay,
with
Terry.
computational. You're amazing, Terry. And the prize for today was CS for Fun Puzzle Book, and also CS50 Puzzle Days. Yay! So you'll be receiving that shortly. And as always, we love to hear feedback. So please let us know how we're doing and how we can make it better.
So I put the feedback form into the chat, and if you could take 1 or 2 minutes to quickly fill it out, we'd appreciate it. And we really thank you for participating today and
Mm-hmm.
sharing your thoughts in the chat and helping us solve that problem with Faith's camera and solving that puzzle.
We love your participation. Thanks for joining us.
Okay, so I'm going to
Thanks.
turn off
That
the
was
recording.
fun.
I'm going to turn the recording off. Stop, stop, stop.